Hi, my name is Derrick Johnson. I'm an engineer here at Qualcomm. Today, we're going to walk you through the step-by-step process of developing an HRNet Pose app. We'll be using Snapdragon X Elite, Snapdragon Hexagon NPU, as well as Onyx Runtime QNN. Let's get started. Okay, so let's get started. Our entry point into creating this HRNet pose detection application is going to be Qualcomm AI Hub. From Qualcomm AI Hub, we will go into models, we'll go to compute because this will be used for the Snapdragon X Elite. Because we're looking for HRNet, this is a computer vision model. This will be pose detection. And then because we want to run on Snapdragon Qualcomm Hexagon, which is our NPU, we need to utilize the HRNet Pose quantized version of the model. We can just download a model, but I also recommend going in, just looking at the research paper, understanding what this model is about, what it's trained on, and getting a better understanding of the model. You can get that from here. You can also get the model repository, which will show a few sample apps and just some more necessary information regarding the model. So we'll go ahead and get started by downloading the model. And we want an Onyx Runtime version. While this is downloading, let's just briefly talk about what Onyx Runtime is. Onyx Runtime is open. Onyx stands for Open Neural Network Exchange. And what this allows us to do is train models in PyTorch, train models in TensorFlow, whatever format that you want to train a model, we can then convert that to a .onyx extension format, and this will allow you to run it on any system. So our NPU, specifically Onyx Runtime QNN, will allow you direct access from the Onyx graph to the NPU, as we'll see as we go forward. So the scope of this app isn't necessarily environment setup. If you do need more help with setting up your environment, I encourage you to go look at our blog walkthrough where it goes through the entire process of setting up the environment, from Python to where to get this OpenCV wheel, everything that's needed to set up your environment. I encourage you to go there to get that more in-depth information. All right, let's get started. So now our entry point into any of this is, because we have so many different environment dependencies and things, that they're actually kind of pain points, because you can do things in the emulated version of Python, but in order to utilize Hexagon, which is this Qualcomm NPU, we need to have a strict version of Python, the one that we allude to right here. So what we want to do first is we want to import platform, and we want to get all of our system information just to be sure that we are in the correct environment. So when we run this, we'll see that, okay, we are in fact using the correct environment. We're on Windows, and now we're ready to rock and roll. If you see AMD 64, you are using an emulated version of Python, and you will not have access to Hexagon. Okay, now before beginning any journey, we need to ensure that we have all of the tools that we need before we can actually get started. This is where we're going to do all of our imports. First import, the most important import for this HRNet pose, is probably, well, one of the most important, they're all important actually, is we need CV2, OpenCV. As I said, as of this recording, this isn't officially supported for this version of Python yet. So what we have to do is, or what I've done, is built from source, and we have a repo that we'll link to that has the wheel already available. You shouldn't have to be building anything from source. That's on us. Then we're going to import NumPy. When you pip install NumPy, there is an official build for this version of Python. And then of course we need our Onyx runtime, and we're going to import that as ORT. And the pip install that you're going to do is pip install Onyx runtime -QNN. This is going to be our gateway into being able to utilize Hexagon. Then we have some other things. We're gonna import image from Pillow, some path cleanup type of a library, pathlib, as well as we're gonna do typing. So let's go ahead and run that. Now the first thing we're going to do is grab some relative paths. The first path is going to grab the path to our root directory. This is going to be where this notebook resides so that we know where to navigate to get to our model, etc. Then we need to find the path to our Onyx runtime. This will be within site packages. So we'll go ahead and run this. And then let's just go ahead and print out root directory. Let's see where we're at. So here we are. This is where this particular notebook lies. And then let's see where this path is. Okay, as you can see, this points to site packages. Site packages, Onyx runtime to be exact. And the benefit of this is that when you pip install Onyx runtime QNN, you automatically gather all of the drivers that's needed to run on our NPU or CPU or whatever processor you want to. This is beneficial because initially you would have to go to Qualcomm's website, download the SDK, find the drivers, point this to the drivers, or go use NuGet, which is a package manager by Windows, figure out how to install the different command line arguments to get things installed. Now it's nicely packaged as one. You pip install, you get all your drivers. And this is the path where where all the drivers are going to be located. One thing I forgot to mention is that after you download the model, you need to put it in the models directory. So after you do your git clone, it's not going to have the model automatically in the models directory. We're going to get our model from AI Hub. We're going to place it into that models directory, specifically HRNet pose subdirectory. And this is what we're doing here. So I'm just going to create a variable, HRNet pose. This is going to be our subdirectory. The model name is the one that we got from from Qualcomm AI Hub. And then we're just going to join these paths together. So let's just go ahead and run this and see what the output is. So now we see from our root directory here, we're going into models, we're going into the HRNet pose subdirectory, and we're pointing this path exactly to where the HRNet pose quantized model is that we got from AI Hub. Now, the next thing we need to do is we have to tell the inference. When we set up our inference session using Onyx runtime, we need to point this inference session to the backend. And the backend is going to be our driver that allows us to control Hexagon. So what we're going to do here is we're going to say, okay, we're going to use our Onyx runtime directory that we got here. And then where is the driver? Well, the driver is in a subdirectory called CAPI. And then this is the driver that we need to point our inference session to so that we can use Hexagon. Let's go ahead and print that. And now we see this will be the direct path to our driver for Hexagon. At this point, we're actually ready to go ahead and set up our inference session. So what we're going to do first is we need to have a variable called QNN provider options. What we're going to do is we're going to say, okay, our backend path, and as you can see, this is just a dictionary, our backend path, and we're going to point to where this QNN HTTP.dll is located. This is the path that we got here. Then we're going to go ahead and start our inference session. So we pass, this is our Onyx runtime, the inference session, we have to pass our model, so the Onyx model that we got here, and then our providers. Now the providers that we're going to use is QNN execution provider. This points to the Hexagon driver, and then we're going to have a CPU execution provider. And lastly, after we set up our QNN provider options, establish the backend that we need to point to, and then we set up our session. Let's get the providers that are available to us. Now, you may run into a case where when you do this, you don't see the QNN execution provider here. What this likely means is that you didn't point to the correct driver somewhere in your path. So I would go back and check the path and ensure that your in-site packages, your virtual environment, site packages, Onyx runtime, and you are pointing to this directory. Because if what the inference session does is if it tries to, it's going to try to use QNN execution provider. If it can't find the driver, then it will default to the CPU. So you just won't see the QNN execution provider as an option. Another possible issue, if you are like, look, I see the path, I see this exact driver, it's at this location. Another thing I would encourage you to check is to come back up here and ensure that this says ARM64. If you see AMD64, you are in an emulated version of Python and you're not going to be able to run the QNN execution provider. So those are the two quick and most likely scenarios where your QNN execution provider will not be available when you begin this inference session. So great, we have our inference session set up. We see that we do have the QNN execution provider available to us. Let's go ahead and explore this model. So let's first explore the expected inputs to the model. And we'll run this. Okay, what does the model expect as an input? Well, because we are using HRNet pose, we know that the model needs an image of some type. What kind of model? Well, it needs to have the dimensions of 1, 3, 256 by 192. What does this mean? So this is telling us that we have a batch size of 1, which it will always be 1 for our case. The number of channels is going to be 3. What information does this give us? This lets us know that these images are expected to be basically color. And then we have 256 by 192 image size. And then the type, we expect it to be float 32. Now we know what the model expects as an input. Let's see what the model is going to give us as an output. So the model is going to give us what they call heat maps. And the shape of these heat maps will be 1 by 17 by 64 by 48. And then of course, float 32 again. So what are these heat maps? Well, if you did read through the paper a little bit, you would understand that what exactly are we trying to predict with HRNet pose? What HRNet pose is supposed to give us, is going to give us, is 17 different key points on our body. So it can be your left eye, your right eye, your left ear, your right ear, your left kneecap, your right kneecap. You're going to get 17. It's going to be able to identify 17 different points on your body. So that's exactly what we see here. Each individual heat map, we're going to get 17 heat maps. Each individual heat map represents a different body part. And you can look at the COCO data set to determine exactly what point maps to which body part. And then, so we'll get 17 different heat maps that correspond to 17 different parts of your body. And it's going to return it in a 64 by 48 matrix. And we'll get more into how does this translate to what we're trying to do as we continue with the walkthrough. Now let's go ahead and get started with the more fun parts. We understand, we did some model exploration. We understand what our model needs to perform inference. We understand what our model is going to give us after inference. We understand how to set up our inference session. Now we're ready to begin having some fun, if you haven't already been having fun. What we're going to do first is we're going to create some helper functions. And this is going to help us when we get into the main application part. This first thing is we need to, and I'm not going to go too in depth because we'll go in depth later. But this first helper function is going to help us transform our image that comes from the camera to shape it into the format that the inference session expects. So the input to this helper function is going to be our original image array, which is going to be in the form of a NumPy array. It's going to be the expected shape, which we got here, which is also going to be this input 0.shape. So the expected shape is batch size 1 by 3 by 256 by 192. And then the output that we're expecting is we're going to return a tuple of 2 NumPy arrays. All right. So essentially what what this helper function is going to help us do is resize and normalize an image using OpenCV and return both a height with channel version and a channel height width format. So why is this important? Because if you remember, our input to our model expects the format of channel, height, and width. So what we have here is channel, we have our height, and we have our width. But what comes from the camera is going to be a version height, width, channel. So here, this is actually a pretty straightforward function. So we're not going to spend too much time here. We're unpacking the expected version. So we're going to get the height. We're going to grab the width. We're going to resize the image using CV resize. We're going to pass the image to this function. We're going to pass the width and the height that we're trying to resize the image to. And then we're just going to do an interpolation. So CV, an intercubic interpolation. Next, we need to cast the type as float32 because that is what our model is expecting as an input. And then another little subtle thing that it actually doesn't mention it in the paper, but to perform inference, we have to normalize the data too. So what we're going to do is we're going to divide all of our pixels by 255 to keep the pixel range between 0 and 1. And then we're also going to, so now we're going to do our transform to get it into this, our transform transpose, to get it into this channel height width format. So we'll take this float image after we've done our resize, we've done our typecasting, and we're going to use NumPy transpose to basically take height, the input height with channel format, and place the channel in front. So now we're going from height with channel to channel height width. And that's what we're expecting. That's what the inference model is expecting. So, and really this, I've grown to call it shape shifting. This is really the most kind of tricky part with developing this because you have to get your model and you have to get your frame and morph it into what the model expects. You can't just grab it from the image and send it to the inference session and think it's going to perform inference. So keeping track of what frame is height width channel, what frame is channel height width, which frame is normalized. This is probably going to be the most tricky part of doing this HRNet pose detection app. So let's go ahead. We're going to see, we will return our original image that is typecasted to float32 and scaled. And then we're going to also return our transposed image or transformed image that's transformed to this channel height width image. Okay, so with this helper function, we basically handled what I'll call the front end on the model, the front end of the model. How do we get our image from the camera and get it in a format that we can use for the inference session or to run inference on the model using Onyx Runtime QNN. Now, let's create another helper function that helps us on the back end of inference, or after we pass the image through Hexagon and we get an output, how do we make sense of this output? And this is where we have a helper function called the key point processor. And the reason I had this NumPy is because initially I did all of this processing in PyTorch, but PyTorch isn't yet supported for our version of Python that we need to use in order to perform inference on Hexagon. So I had to convert all of the PyTorch code to NumPy. So that's why you see this NumPy on the end, NumPy right here. So anyway, let's get back to this helper function. What are the inputs that we expect? Okay, so we have a post inference array, which is going to be a NumPy array. We have our scalar height, our scalar width, and then we're going to return a tuple of 2 ints. We'll get into the scalar height, what that means. Maybe we'll get into it here. Let's see where it goes. So what is the overall purpose of this helper function? Well, as I said, we handled the inference, the model transfer, the image transformation to run into the ultimately hexagon, now we need to handle the post-processing part. So this helper function is going to extract the key point coordinates from the individual heat maps, scale them, and then scale them to match the original image dimension size. So what we do here is we just create an empty array initially, and now we're going to iterate through all 17 heat maps. So remember that once we do our post inference, what we're going to get back is we're going to ultimately get something in the form of 17 by 64 by 48, 17 different heat maps. So when we iterate through this post inference array, we're going to say, okay, at some point, this key point is going to equal 1. We're going to grab that index, that heat map, store it in heat maps. Now, what we're going to do is we're going to find the maximum argument, the index of the maximum value within this heat map. And what this tells us is that for this particular, so let's say the heat map is going to be a heat map that corresponds to where our eyeball is. That max point within that heat map is going to be where the model believes is, or where's the highest probability that the eye resides. The left eye, the right eye, knee, same thing. Well, the eye and the knee isn't the same thing, but it's going to be the same concept. So once we grab this index, now we're going to use this index to actually get the location of where that left eye is located. So that's what we do here. So we're going to unravel this. We're going to pass this index where that maximum value occurs. And then we're going to grab the image height, the image width. And then for our final coordinates, what we have to do is remember that. So ultimately, remember how I said we started off with an image, the model expects an image of 256 by 192. That's the size. Well, within the model, it scales it down. It scales that image, divides it by 4, the height and the width. So what we do here is we basically are going to unscale. I don't know if that's a word, but we're going to bring it back to the original image height. So after we do the inference, the heat map is going to be in the form of 64 by 48. We're going to take wherever the image height, where it said that it found the left eye, the location of this left eye, for example, and then we're going to multiply it by 4 to bring it back up to the dimensions that we're expecting. So 256 by 192. Then I store this into this empty list. So we should have a total of 17 different coordinates. And then we're going to return this. Okay, so here we are. We're at the finale, almost at the end. We've grabbed our model from Qualcomm AI Hub. We've created our Onyx runtime QNN session. We pointed that session to use our hexagon driver or QNN HTTP.dll. We pointed the inference session to the model. We've created some helper functions to help us with the pre-processing of the image before it goes into the model for inference, and then the post-processing after the model has performed inference. And we've also done some general housekeeping where we inspect what the model needs, which maybe is probably the most important part, because we need to know what the model expects as an input, what the model expects as an output. That's the meat of everything. Everything from here on out is going to be pretty straightforward. So the first thing that we're going to do is we're going to instantiate this video capture object from CV. When we pass 0, you can pass 0, you can pass 1. Passing 0 will default to whatever your system camera is. So basically, if you're on a Snapdragon X Elite, it will use that front-facing camera when you open up the laptop. If you have a webcam plugged in, then you may use, say, 1 if you want to use that. We're just going to use the system camera, and then we're going to do just a quick checker to make sure that you have the valid camera selected. If it can't open the camera, if you have a 1 here and you don't have a webcam plugged in, then you're going to get an error. But because we're all using Snapdragon X Elite, you can just use 0 and use that camera that's built in. So now we've opened up our camera. Now let's handle our scaler. Now, initially when I did this, I didn't realize that the image that HRNet Pose just used a scaler of 4. So I went through this full operation to determine the scaler, only to realize later on by reading a paper on that wasn't even related to HRNet Pose that the scaler is 4. So we'll just get it dynamically here. So once again, we're grabbing our expected shape, the second and third index. So this is going to be the height and the width of the expected model input. And then the heat map, the heat map height and width that we already already beat this with a hammer. 256 by 192, 64 by 48 for the heat maps. Determine the scalar for the height and the width by just dividing. And then of course, in this function to get the original image back, we multiply by this scalar. Pretty simple. Now let's enter our while loop. Now the purpose of this while loop is we will continuously capture frames at whatever speed that our image is able to capture frames at. And we're going to read that image. So remember, we opened up the camera here. Now we're going to use that to keep on reading images as fast as we can. So once we get this capture read, we'll now have a frame. What this capture read is going to return is whether the return happened. Were we able to capture a frame? Because if we aren't able to capture a frame, there's no need to proceed. So as I alluded to earlier, it's very important that we keep track of whether our current frame, our current image is height width channel, channel width height, channel height width. Is very, because if you don't keep track of that, you're going to get lost. It's inevitable. And then you're going to be spending multiple time printing dot shapes to understand exactly what your input is, and then trying to understand where you're trying to get to so that you can perform this inference. So once we do the image capture, we'll get the frame in the format of height width channel. And then we'll get this, like I said, we'll get this return value. And then we'll just do a quick check, because if return isn't true, if we weren't able to capture an image, then it doesn't make sense to do anything else. So we're just going to break out of this while loop. Now comes the first use of one of our helper functions. This will be the helper function that transfer numpy OpenCV, where the input is going to be this height width channel frame that we got from our image capture. And then also we're going to pass our expected shape. What does the model expect? Because remember, what we're going to do with this image is we're going to resize, we're going to scale, and we're going to typecast. And we're going to resize based on what the model expects. What do we get from from this helper function? Is we're going to get a frame in the format of height width channel. And I call this height width channel frame processed. And you may say, hold on, you already have the height width channel frame from the capture. Why are we doing this again? Well, because remember that we need a scaled down version. So we're going to scale this and we're going to resize this. Yes. So that's why, because it's actually a different image after we pass it through this helper function. And then we're also going to return our channel height width frame. And remember, this channel height width is going to be the format that the inference session or that Onyx runtime QNN or that the HRNet pose model expects. Almost. We'll have a few more things we have to do to this image to really get it in the exact format, but this is the start. As I said, we're almost ready for inference. There's still a few more things that we need to do, or actually one more thing, before we can actually pass this to our model. Remember that we needed, for our model inference, our model expected an image size of 1 by 3 by 256 by 192. Well, this image is going to return a channel height width. When we do this transformation, this will still be channel height width. Okay, hold on. Let me back up. Our capture read is going to give us an image of height width channel. After we pass it through our helper function, we're going to get a frame that we expect to pass to the model of channel height width. But we're still missing one dimension, because remember, our model is expecting batch size by channel, by height, by width. So that's what we're doing here. We're just going to expand this by one more dimension, so that ultimately what we end up with here is 1 by 3 by 256 by 192. And this is what our model expects as an input. So this channel height width frame, just to make it more concrete, is going to give us basically just 3 by, man, what comes out? I'm not even 100% sure how the actual size of the frame that comes out of the capture, but let's just make up something. Let's just say 256 by 192. This is the format of channel height width. We're going to get 3 by 256 by 192. Actually, that is right. But that's not what the model expects. The model expects this batch size to be added to it. So this is the final little piece before we can have fun. The final hurdle. So now we've got our final frame, and we are ready to finally perform inference on Hexagon. We have built up to this point. We have gone through all of the pains of the environment setup. We've gone through setting up our paths. We've gone through grabbing the model. We've gone through inspecting our model, creating our helper functions, making sure we're using the right camera, and we're finally here. And this is all it is. You run your session, you pass in the inference frame, you get an output. It's kind of anticlimactic, but that's what we have. You are now running on Hexagon NPU. And remember that this is going to do this for every single frame. As fast as our camera can capture frames, it's going to be performing this inference on Hexagon NPU, which I guess that is pretty cool. But this is it. This is going to send the model, is going to send our frame to the model. The model is going to perform inference on Hexagon, and it's going to give us our outputs. There you have it. So what's expected from after we run our inference session on the frame, we get an output of, we get an output. We do get an output. But we also have to do some pre-post processing before we can pass it to our helper function. And what you see we're doing here is we're calling this squeeze twice. That's because after we perform inference, we get our output is going to be in the shape of 1 by 1 by 17 by 64 by 48. We know what 17 by 64 by 48 is. We don't need these two ones. We need it just in this format. So basically what I'm doing here is I'm just taking off those extra dimensions. So ultimately what we end up with is 17 by 64 by 48. Now we're ready to pass to our helper function. The helper function is going to take this output tensor, is going to take in the scalars that we determined up here, which are just 4, and we're going to return the coordinate list. And the coordinates are going to be the coordinates that the model predicted of the different key points or the different body points. So each body point is going to have a different coordinate. That's what's going to be returned in this list. We're almost on the home stretch. Now what we're going to do is we're going to go back to our this height width channel frame that was pre-processed as part of this as part of our helper function. And we're going to scale this back up so the pixels. So remember, we normalized it within our transform, and to keep all of the pixels within the range of 0 to 1. Now we're going to scale those pixels back up, multiplying. We're going to multiply them by 255, and then we're going to cast this as an unsigned int8. The reason that I do this frame.copy is because sometimes when we do this work on these frames, you'll get this segmentation fault error. So this gets rid of that. So you just copy it, it gets all the memory back how it's expected, and you don't have this segmentation error. So now we have our original frame scaled and typed to unsigned int8. What we're going to do now is we're going to use our coordinate list to map each point, all 17 points, based on the coordinates that we retrieved from the inference. We're going to map those back to our original frame, which is here. So that's what we're going to do here. We're going to go through our coordinate list. We have a tuple of the y and the x, and we're going to say, hey, place a point of radius equals to 3, of color 0, 0, 255. This is RGB, so this will be red, and then of a thickness of -1. Place each one of these points on this image. Now we're going to resize the image again. Oh, okay, so the input size that I was struggling with up here, the image that's captured from OpenCV is going to be of size 640 by 480. So here we're taking this frame, which is going to be 256 by 192, and we're going to resize it again to 640 by 480. We're going to show this frame, and then this is just something part of OpenCV where if we press Q, then it will exit the frame. So as you can see from running this frame, we're now performing inference on a real live image or images where we can see those distinct key points being mapped to the different body parts that we're performing inference on. So the 17 different key points, 17 different body parts. So let's just recap everything that we did to get to this point. We first got our Snapdragon X Elite computer to be able to utilize the Snapdragon Hexagon NPU. You now see how awesome the Snapdragon Hexagon NPU is, and how for any type of inference, you should be using the Snapdragon Hexagon NPU. You got a quick tour of our AI model hub, where we grabbed the HRNet quantized version of the model. We then went through and loaded up our Onyx runtime QNN. We got all of our dependencies. We loaded up Onyx runtime QNN. We created our inference session. We did a lot of different we did image transformations to get it into the format that we need. We understood what the model input expectations were, as well as what the model the expected outputs were. We created our helper functions to pre-process and post-process the inference. Then we created a simple app that utilizes HRNet pose to perform inference to do pose detection, which was the ultimate goal. But we're not done yet. Anytime you see my face in one of these videos, expect a little something more, a little added bonus, a real-world application that connects these 17 different points on the body to something that you can do in real life. What I have created here is just a simple yoga pose detection app based on the HRNet pose application. You can see as I move through these different positions, it's going to be able to identify that position and then display the position to the screen. From here, this is just the beginning. I can imagine where you have maybe a dance detection, a dance sequence detection, maybe a physical therapy detection to help you with physical therapy, getting into different positions and ensuring that you are in that correct position. I hope you found some inspiration, and I encourage you to just go and explore and create and develop using Snapdragon X Elite in hexagon. Have a great day and hope to see you again.